Hello! In this video, we are going to prove the following theorem. For every complex number a, 0 times a is equal to 0. Now in this series, we are looking at a list of axioms for the complex numbers. These axioms come from MetaMath, and I'll have information about that and the axioms in the description below. So let's remind ourselves what we're working with. We are given a set C called the set of complex numbers. We're given a subset of the complex numbers R called the set of real numbers. We're given 3 elements of the complex numbers, namely 0, 1, and I. We are given 2 binary operations on the set of complex numbers, addition and multiplication. So given any 2 complex numbers a and b, we have that a plus b is a complex number and a times b is a complex number. And finally, we are given a relation on the set of real numbers called the less than relation. So given any 2 real numbers a and b, it might be the case that a is less than b, and we write this. Otherwise, a is not less than b. Okay, and from here we have a list of axioms, which I have listed down in the description below. Now in proving this theorem, we are going to be using several of those axioms, including the following. We're going to be using axioms 1 through 8, and also axioms 11 and 12. So let's remind ourselves what these axioms are. Axiom 1 tells us the sum of any 2 real numbers is a real number. Axiom 2 tells us that the product of any 2 real numbers is a real number. Axiom 3 is the commutative law for multiplication. Axioms 4 and 5 are the associative laws for addition and multiplication. Axiom 6 is the distributive law. Now axiom 7 tells us that 0 is equal to I times I plus 1. Axiom 8 tells us 1 is not equal to 0. Right, we're also going to be using axioms 11 and 12. Axiom 11 tells us, for any non-zero real number a, there exists a real number x such that a times x is equal to 1. Now axiom 12 tells us the following. Given any complex number a, there exists a pair of real numbers x and y such that a is equal to x plus I times y. Also, in proving this theorem, we are going to be using all of the results that we have proven at this point, which is that 0 is a real number, 1 is a real number, right? So we've proven these 2 facts. We've also proven the left cancellation law of addition for real numbers, which says the following. Given any 3 real numbers a, b, and c, if c plus a is equal to c plus b, then a is equal to b. And we've also proven that 0 plus 0 is equal to 0. Okay, so now we're going to prove this result. But actually, we're first going to prove for every real number a, 0 times a is equal to 0. So we're going to prove this lemma first. So, to start the proof, let's give ourselves an arbitrary real number a. And from here, we want to show that 0 times a is equal to 0. So let's assume for a contradiction that 0 times a is not equal to 0. Now remember, 0 is a real number, a is a real number. The product of any 2 real numbers is a real number. So 0 times a is a real number. Therefore, 0 times a is a non-zero real number. So we can apply axiom 11. That tells us that there exists a real number y such that 0a times y is equal to 1. And now we're going to take advantage of the fact that we've proven 0 plus 0 equals 0 to manipulate what we have here. What we can do is we can replace this 0 with 0 plus 0. So in that case, we have 1 equals 0a times y, but we're going to replace this 0 with 0 plus 0. So this is 0 plus 0 times a, right? All of that times y. And we have the commutative law for multiplication. So we can flip 0 plus 0 and a around like that. And then we have the distributive law, so we can distribute the a across this parentheses. So we get this, but then we have the commutative law for multiplication again. We could flip a times 0 to 0 times a times 0 to 0 times a. So we get this. And then, applying the commutative law of multiplication again, we can move y to the front of this parentheses, right? And then we apply the distributive law, distribute y across this parentheses. So we get this, but then we apply the commutative law for multiplication again. We can swap 0a and y, swap 0a and y. So we get this, but 0a times y is equal to 1. So this is just 1 plus 1. So what this shows is that 1 plus 1 is equal to 1. Okay, so then what can we do from here? Well, we're going to take advantage of the fact that 0 is equal to I times I plus 1. We're going to replace this 1 with 1 plus 1, since they're equal. And then by the associative law for addition, we can move these parentheses around I times I plus 1. So we get this. Well then, I times I plus 1 is equal to 0. So we get 0 plus 1. Now remember, we've proven that 0 is equal to 0 plus 0. So this shows 0 plus 0 is equal to 0 plus 1. Now remember, 0 and 1 are real numbers. So we're in a position where we can apply the left cancellation law of addition for real numbers. Canceling out the zeros, we get that 1 is equal to 0. But this contradicts Axiom 8, which tells us 1 is not equal to 0. So we've reached a contradiction. Our assumption that 0 times a is not equal to 0 led us to a contradiction, so we must instead have that 0 times a is equal to 0. And so this proves our lemma. So we have proven for every real number a, 0 times a is equal to 0. Now we're going to prove for every complex number a, 0 times a is equal to 0. So now to prove our theorem, let's give ourselves an arbitrary complex number a. And from here, we're going to show that 0 times a is equal to 0. Now, applying axiom 12, we know since a is a complex number, there is a pair of real numbers, I'll call them x and y, such that a is equal to x plus iy. So now, what happens if we do 0 times a? Well, replacing a with x plus iy, this is 0 times x plus iy. And then applying the distributive law, we distribute 0 across this parentheses. So we get 0 times x plus 0 times iy. Now, by our lemma, 0 times any real number is 0. So in particular, 0 times the real number x gives us 0. So then what about 0 times iy? Well, I'm going to save us the trouble, but really if we manipulate this, since we have the commutative law of multiplication, we can flip 0 and iy around, so we get iy times 0. And then by the associative law for multiplication, we can move these parentheses around y times 0. And then, applying the commutative law of multiplication again, we flip y and 0 around. So that becomes 0 times y. But we know that 0 times any real number is 0. So in particular, 0 times the real number y is 0. So this comes down to I times 0. So I'm just going to write I times 0. Now remember, we're trying to show that 0 times a is equal to 0. So it suffices to show that 0 plus I times 0 is equal to 0. So how do you suppose we show that? Well, the trick is we apply axiom 12 to the complex number 0. Since 0 is a complex number, there must exist a pair of real numbers I'll call s and t, such that 0 is equal to s plus it. But then what happens if we multiply both sides by 0? So 0 times 0 is equal to 0 times s plus it. Now if we distribute 0 across this parentheses, this becomes 0s plus 0 times it. Since 0 times any real number gives us 0, 0 times the real number s is 0. So what about 0 times it? Well, it's exactly the same argument that we use to show 0 times iy is equal to I times 0. So 0 times it is going to be I times 0 once again. But remember, 0 plus I times 0, we showed that that's equal to 0 times a. So this is just 0 times a. And so, well, what else? Remember, 0 times any real number is equal to 0. So in particular, 0 times the real number 0 is equal to 0. So this shows 0 times a is equal to 0. And so, we're done. That's it. So this completes the proof. And so yeah, that's pretty much it for this video.